Today, let us discuss a few solved problems from synchronous machine. So let us start with the first problem. So, what first problem state uh, that we have a three-phase star connected. As I am taking problem from few very old book, so means using an e-scan software may give us a very poor resolution. What is R? That is 0.5 ohm. ISC is equal to 200 ampere. IFSC, that is the current at which this 200 ampere flows through armature circuit, is 40 ampere. This much current should be circulated through your field winding to ensure this 200 ampere. Okay, and this IFSC is also sorry. This 40 ampere field current gives us, we can write that uh, voltage VOC with IF is equal to 40 ampere is equal to 1000 volt. Now we have to determine the synchronous impedance. What is the value of ZS? That is the question. And thereafter we have to compute power angle, delta, and also percentage regulation. So here let us start with this, how to find out what is the value of your means synchronous impedance. That is, since this is star, that is why this root 3 factor is coming. So what we will get, that like ZS is two way you can do it, like you can have something like 1 upon your SCR in per unit value, or you can directly figure it out. So what is the value of ZS? ZS is equal to and what about XS? That will give you 3.14 ohm. So what about terminal voltage per phase? Rated terminal voltage will be 2200 by root 3 that is. So what is the formula? E naught is equal to V plus I R plus JXS, and you know what to do, that is this is because of that 0.6, and so if you do it, you will eventually get so amount of regulation. I have not checked the calculation from the book, but I think it's correct. You can check all the numerical values by yourself. Okay, so heading towards our next problem. Our next problem says it is a 2000 kVA, 11 kV, 3-phase Y connected alternator. Per phase resistance is problem number 2. Per phase resistance R is equal to 0.3 and X is equal to 0.5. Mind that this one is actually XL plus XAS. So it delivers full load current at power factor 0.8 lagging. Full load current we have to calculate. So at normal rated voltage, we have to compute the right. Actually, all these are like that kind of transformer problem. Beauty of the problem will start when you will go to a situation where you have to deal with actually means nowadays for these two problems it can be solved without having a very in-depth knowledge in electrical synchronous machine, but I'm going to discuss 15-16 problems, and here where I would like to highlight that how this is different from that transformer problem, as well as where do we need more means insight and knowledge and be more careful with our decision. I'm going to discuss all this, and I accept all your requests for 1 hour video. If majority wants, there is no problem for making, but means sharing problem sources for every video, that is like, since I have to handle it single-handedly, in MIT, it's good that they supply problem sheets, this, that, for each and every topic. But for me, single-handedly, then like if once I have to sit and compile a question paper, it's easier for me. But if I have to do that for each and every chapter, then it would become a bit means time-consuming task for me. Unfortunately, I do not have that much time because I'm already overloaded, and this time also I have to take one third year course, one back to back to BTech course, and both of them are 4 credits. So you can understand the pain. Anyway, so that here the terminal voltage per phase is how much? It's like current, we can figure out I do not know, I am copying from some book, but how it is very surprising that it gives you round about 105, means it must be a round up figure. It cannot be the case because in the denominator you are having such a thing, and in numerator you are having this. Well, so I'm not considering the numerical value, rather I'm more concerned with the approach. So then you do this. And you get something like instead of copying each and every steps, let me write the final equation what they are having, that is 6. So very important here, this is your delta. In the last problem, I think I have forgotten to mention. Here, this much is your delta, the power angle. So now we have to do it for the leading power factor. Obviously, in case of leading power factor, what would happen? Like it will become so what we will have here, right? Remaining things remain same. So if the remaining things remain same, what you will get here, you will get something like that is the V, what they have calculated, it is coming something like oh sorry, V we have to determine, sorry, I made a mistake. Right, that is why I couldn't figure it out. Yeah. So what we have here, we are having V minus 289.8 plus J 438.9. Right. So if you see this, what you will get, you can use that triangle law, or means what you can do it here is that doing something like that same kind of transformer manipulation what we used to do. So what you will get here, it's like now value of V, this one we know because in that last example we find it out, it was this much, so we just need to put it here. Because in this problem it has mentioned that we have carried out with same IF. So if IF remains same, then your E naught, do remember E naught is free from armature reaction. When you give a capacitive load, it has an effect of kind of means magnetizing action, and reactive load means inductive reactance gives us a demagnetizing action. Rest of the things remain same. So if this is then what you should get here, your V will become again, I am telling you, I am copying from some book, so please check the result. Last year, means last year also, and also in last semester, there was a problem of transformer unbalance load, which I took from the book of A.S. Langstroth, and I copied the solution as it was there. And the solution seems convincing, but then one student, probably Ayushman, what is his title, Ayushman Khurana, he said that so Mr. Khurana pointed out it was like the case was not correct. Even in that Langstroth, the book, authentic book like Langstroth, it was some typos was there. And although what he calculated, it was not that much, means the numerical figures were not very convincing, but then I cross checked it and I found that yes, his calculation was correct and what was given in that book was wrong. And it took me some time to digest that fact that even in book of that standard they made that kind of typos, because that book was published in 1956 or sometimes. So at that time people used to be very meticulous with what they are writing and with their choice of word, with their calculations. Although at that time power of means calculator or computing devices were poor, but means so the moral of sharing the story of how Ayushman Khurana corrected me and how it was, it's that very simple thing that It is like, means don't trust anything, just take the problem and solve it by yourself, follow the calculations. And I wish I could have that kind of means timestamp inserted here, but unfortunately, as I said, that I have to do everything single-handedly. So means uh, planned a lot of things, but couldn't execute because of shortage of time and resources. Because it is not that like I sit and everything is over. It is that sometimes I need to practice, sometimes I need to not practice really, rather I need to just survey the books, what are the problems they are giving, what more insightful problem I can extract from some other sources, and in that means circle I couldn't get enough time to cross check and validate everything. And sometimes, as I said, although right now I think the I do not need, because those who means during that first semester where I was doing that type of things, I should not repeat here, because now you are quite seasoned, and those who are not yet, means those who have not yet been seasoned, it is difficult for me at least to season them. So let us move with the rest of the people. So if anyone is interested to doing this kind of video editing, they are open to share their thoughts, and then I will grant them the permission of editor, so they can insert the timestamp. So a student can get to know that suppose at 13.15 I have discussed a new problem. So if he or she is done with that first problem, then he or she can directly go to 13.15 to see the next problem. And likewise, but unfortunately here what is happening, that you have to wait until one problem, even you yourself can do that problem, have to you have to wait till the end. So that if you people are kind and means willing to help, then you can please let me know, then I can grant you the permission to do so, that kind of editing. So this is surface voltage, and obviously what about the line voltage? That will be root 3, as it was star connected things. Now so in our next problem, what it states that we are having uh, this one is somewhat good one. Problem number 3, 3-phase, 2-pole, 6000 volt, 3000 RPM. Now, one thing I would like to mention, that as in India we are dealing with 50 hertz. So, whenever we mention 3000 RPM, even if frequency is not mentioned, you can assume it is 50 hertz. If it is a two-pole machine, then obviously 50 hertz. Like few things goes hand in hand, like two-pole 3000 RPM 50 hertz, four-pole 1500 RPM 50 hertz. It's like that. Has 60 armature slots with 4 conductor per slot. This is the real problem, and effective resistance and reactance is 0.1 and 2 ohms. This is obviously part phase data. Now, the open circuit characteristics is here. Let me insert a picture. This is the open circuit picture. We have to determine the regulation at power factor lagging, right? So this is the car or field ampere. Now you think about it, then we'll solve. Before I start, think about it. If you want, you can go to the previous fundamental of rotating machines video to figure out how to assemble this data to solve the problem. Well, so let us get started with this. So three phase, two pole, blah 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 blah. Now we are all ready to solve this problem. So first, to do the simple thing, that is what is that most simple thing that you all know, to find out the terminal voltage VT, V, whatever you want to call it. And this gives us the full load current, that is something six by, I do not know how this is coming, as I have already mentioned that I do not get time to check the calculation like Ayushman Khurana did in last semester. You people can also check the calculation by yourself and let me know if there is any mistakes. I will try to rectify, because I have taken this from different books, different uh, means places, so it is quite possible that I can make mistake. So now it is our induced EMF, not open circuit EMF, induced EMF. So what we are getting here is something like, it's like that 381 not plus 175, power factor as usual 0.8, so 0.8 minus j 0.6, and this one is like 0.1 plus j2. Yeah, so now as per their calculation we should get something like that lead us to right. So before I proceed further, let me draw the phasor diagram for your ready reference, because having a phasor diagram would be helpful for us. It's actually very easy to draw the phasor diagram. It's not a big deal. I'm just drawing a very crude, rough freehand diagram. So this gentleman is 3810. This is 175. This angle is cos inverse 0.8, and this person is 4043 3.82. So this is 40. This angle is 3.82. All right. Oh, sorry, I have made a mistake. Yeah. So now we need to draw the your MMM. So if this is our E, then correspondingly what we will get here, we will get if R, then this is our A. So if we subtract minus A from this, we should get if not, this we need to find out, and from that if not we can calculate further. So here the task is like, well, let us do this. What is there? The task is like, now we have to figure out the armature reaction MMF. So armature reaction MMF will be how much? It is, as per our previous formula, it's 0.9 kb kp I. Right. Now what is the information given? N, that is the number of turns per pole per phase. 4 conductor per slot. So if 60 armature slots with 4 conductor per slot. So how to figure out? N will be number of turn per pole per phase. So 60 into 4, total 60 slot, 4 slot per conductor, total 240 conductor. Now 2 pole and 2 conductors are required to form a turn, single turn. So this we are getting is 60. Now kV you can calculate, that is coming it's always same, like whenever it is always You just need to find out the number of slots per pole per phase, right? What I'm trying to say, how this 10 is coming, this is coming from that number of pole, number of phase. So this gives us number of slots per pole per phase, and that will help you to proceed, because this always we always consider it is designed for means narrow spread coil, so it is sine 30 degree, then 10 sine 3 degree. So that is perhaps those who are watching may get confused by this time, and it's getting it difficult, finding it difficult to understand. So that is why I suggest that please go back to the previous video and check it. So what is A? If you put all the values in this formula, obviously N should be there. I missed that N. You will get, it is like 9025 ampere turn per pole. See that seemingly simple problem, how it is getting difficult when I try to fit the problem or try to solve the problem by means of actual data, right? So now here it is very simple, that now we need to calculate the current IF. For that, the fundamental field element, we can use this formula that I showed you, that it is like let it be AR, otherwise you will get confused with armature reaction. But this is not the armature reaction, rather it is the ampere loading of the rotor, that is NZIF by 2. Now see, we need to find out these data also. Okay, I just forgot to write a part of that problem also. Let me write. That was no harm, so I started proceeding. Yeah. So what was that part of that problem? Like here, the other information that I have missed while writing this, there are rotor slots per pole. With angular pitch 10 degree and 20 conductors per slot, right? This information I missed. So now 10 rotor slot, 10 degree, 20. So here it is how much? That is 10 into 20 by 2 into what is the value of IF? We do not know. It is, let it be 100 IF. So what is KB? KB is so here interesting to note that this is a field MMF we are considering and we are applying this formula here. So what we could find out from here is that it is giving us 0.879. So your total A will be this much we are getting. KP is 1 because coding is not mentioned. Now see the process. What was your armature MMF? Armature MMF was where I calculated. Yeah, 9025 ampere turn per pole. So from this we will get the value of IF or means because one is at in terms of IF, another one is at this much. So we can write MMF that is giving us 80.7 ampere. So what about that value? This is the corresponding MMF in terms of field scale. So then it would become something like now we need to know IFR. How to figure out IFR? We have figured out this gentleman is 4043. So for that we need to find out the proportional value of current that should be circulated through the field current. So how to find out that proportional value of current that is responsible? Here from this curve we can figure out the value of current that is required to produce 4382 is somewhere here. Like this much is 4500. So if we draw it, it's like You can take any value between 20 or 215 to 225. So take that value. So this much is, let's take it 215 square plus that one was how much? 80.7. Oh, sorry. Cos this angle we need to figure out what is this angle. This alpha is how much? This is actually angle, this angle. This is our alpha. So if this is our alpha, how we can figure out? What was those trigonometric formula? Anyway, I have forgotten, and hopefully you too. Not to worry much. This one is something like, okay, well, I think I have figured it out. See, if you form a triangle like this, then what you will get is like oh, just a minute, let me figure out how to calculate this. Oh yeah, these two, this person and this A, they are what I'm trying to say, this angle and this angle, I think they are corresponding angle, right? Because these two lines are parallel. So if these are corresponding angle, then we can figure it out by measuring this angle. We can figure out the angle between A and FR. So what is that? That much is your cos alpha is something like 90 degree plus 3.82 plus that cos inverse 0.8. So what you will get is something like, doing all these things and neglecting the negative current, you will get one interesting question, that if I try to if I just reverse the flow of current through my field winding, what changes do you expect? Means it's a DC current flowing through our field winding. If I change the current direction, what changes do you expect? Well, so this is giving us IF naught. Now for this we need to figure out the corresponding value of from this. So it is 274 problem with this whiteboard is that I cannot draw straight lines. So this much, how much this would be? Let us take 4,500. Make it simple. The meat of these two. So your regulation will be so it is your task to figure out that how much accurate this result is, and if I have done any kind of approximation where I did it, because unlike that exploiting that linear relationship, like as it was this much, so it is I have not done like for 4043 it is 215. So now how much it could be for 275, I have not done that, like 274.5 or 275 whatever we are getting. I am not doing this. Like what I am trying to say, that I have not done this in our calculation, right? I have figured out it from car. So it is your task to find out that uh, whether I have made any approximation here at all, and if I have made any approximation, then what is that approximation? Okay. Okay, now let us move to our next problem. Now I would not like to take the problem on salient pole machine before we completely discuss our topic on cylindrical rotor machine. So let us discuss one more problem. The open circuit characteristics of 2.5 VA 6600 volt alternator is given in like one picture we need to insert here. Yeah. So this is our alternator with this is our open circuit characteristics. So now it is 2.5 into 10 to the power 6 VA 660 volt. Y connected, then full load short circuit current obtained at a field current of 30 ampere. So IF is C is equal to 30 ampere. This is field current. R is equal to 0.5 ohm. Then the leakage reactance per phase is 3.4 ohm. So what we need to do here, we have to determine the regulation for 0.8 power factor lagging using EMF method, MMF method and ASA or modified ASA method. I will discuss what is that. It's just a little variation from MMF method. Also, we need to find out the short circuit ratio of the alternator, and another last part is that we have to determine the range of field current, range of IF using ASA method to ensure rated terminal voltage when power factor is varying from 0.5 lead to 0.5 lag. So first try to understand the problem. Some data are given related to that open circuit, short circuit, and you can calculate the rated current. Then we have to figure out the regulation for a particular given load at 0.8 power factor lagging using EMF method, MMF method and ASA method. I have not yet discussed ASA method. What is ASA method? I am going to discuss it soon. Once we got a clear picture of MMF method, then only we can discuss ASA method. Otherwise, the discussion of ASA method won't make much sense, right? So once we discuss that what is the MMF method and solve a problem on this particularly, then you will be able to get more on ASA method. Now here we have to figure out the range of field current using ASA method to ensure rated terminal voltage. So whatever voltage, say it is 300 volt or 3000 volt, whatever voltage voltage specification is given, we have to maintain that terminal voltage. However, the load current will vary, load current will keep, magnitude wise load current will not vary, it will be the full load current, but load power factor will vary from 0.5 lead to 0.5 lag or 0.5 lag to 0.5 lead, whatever you want to understand. But the essence of this problem is that we know that magnetizing current, leading power factor is a tendency to ensure negative regulation. That means you need to, if you want a constant voltage, actually you need to cut down or decrease the amount of field current flowing through your field winding. And in case of lag current, it is producing a demagnetizing effect, so you need to boost your field current to compensate that one. So we have to find out the range, that maximum boost to maximum means weakening. What is the range of that we need to find out in this problem. Okay. Now here, so here we need to first solve this for EMF method. So let us do this for EMF method. Actually, I am interested in recovery of few terms that was there. I do not know what happening. Just a minute. Well, now it is somewhat for 0.8 power factor lagging. So we have our card with us. Now this one. Now we have to go for solution of that problem. So let us go there. Well, so first calculate the terminal voltage. It is 6600 by root 3, that is 308.10 volt. Fine. Find out the full load current. To make it means look it different from the field current, I can write I capital F capital L. So that will be 2.5 into 10 to the power 6 by your 3 into 308.10. That will be 218.7 ampere. So we have to do it for EMF method. So field current at IF is equal to 30 ampere. What is the voltage it produces, that we need to check. So at 30, what is the voltage? So at 30 degree, so this is our at 30 degree we are getting this point. here. So what is the value of this voltage? It is likely, as per the book has taken, it is 7160. So let it make it 7160. So your synchronous impedance that is 18.9 ohm, right? So if it is 18.9 ohm, so what is the value of synchronous reactance? That is equal to again it is coming 18.9 ohm, almost negligible your excess. Okay, now we have to figure out the open circuit voltage for this corresponding open circuit voltage, not open circuit voltage, rather we must say corresponding open circuit voltage for that 3810 plus into it will give you 0.94 degree, right? So if this is the case, then what about power angle? Power angle is 26.94 degree. What about regulation? Very high value of regulation is coming. The value of regulation is going to be as I said in the third semester, Mr. Ayushman Khurana spotted a very good, means made a very good observation. He spotted a calculation mistake. So you will also please calculate by yourself, and in case of any problem, you please get back to me so that I can also help you. So this is for our open circuit test, that EMF method. Sometimes it is also known as the method of synchronous impedance. So this gives us a regulation value 87.8. That is quite a high value, undoubtedly, and means obviously you would not like to go with such a machine that is offering such a high value of regulation, because if the regulation value is this high, it actually indicates that your machine performance wise reliability is very poor, like until unless it is employed in closed loop where you have some mechanism to adjust your field current according to the variation of your terminal voltage, your machine is very sensitive with respect to your like your synchronous impedance. Sorry, your machine is very sensitive with respect to your load. Now let us go to the second part. Let us try to find out the MMF method. So let me go to the next page so that I can draw the phasor diagram that we are going to use for MMF method, because until unless a clear phasor diagram is available with us, it is not possible for us to understand and means comprehend the problem completely and correctly. So let me draw the phasor diagram for MMF method. It was already there. I think if I go back, I can figure it out. Just a minute. It's for MMF. How this happens, that I think I have discussed MMF method, or it seems I have forgotten to discuss MMF method. Not an issue. I'm going to discuss it now. Not a big deal. So in MMF method, what we do is that uh, now here, first draw from this line. I'm a bit surprised that how I missed to discuss MMF method. Anyway, not a big deal. Okay. So first we start with the phasor of V and I. The terminal voltage and load current. Then we draw IR. Actually, what happens in EMF method for a virtual non-existent EMF, for a physical MMF, that is armature reaction MMF, we consider drop across a virtual non-existent reactance, drop of EMF across a virtual non-existent EMF. That is why it earned that name EMF method. Now, what in case of MMF method, we will do the reverse thing. Instead of replacing MMF by EMF, here we will replace EMF by MMF. Let us see how. Now, as I said here, we will do just the reverse. Reverse in the sense, just a minute, let me check whether it's recording or not. Yeah, it's recording. Well and good. Now, instead of finding out or replacing physical MMF by EMF, like EMF method, here in MMF method, we replace physical EMF by virtual non-existent MMF. So V plus IR, if you add these two, the drop across them is a physical EMF. It's a physical EMF. That physical EMF, we draw a vector corresponding to them, adding this V this is the vector I am talking about. This is our V. There is some problem always. Just give me a minute to draw the vector. Yeah, so this is V, this is E. Now for this E, perpendicular to this E, what we have drawn? We have drawn a physical MMF that is responsible for production of this one E. So we draw it at an angle 90 degree. Now, once we draw it, what we are having here? We are having our this, you can consider this one is like if R1 and this being, let it be E2 because we keep E for this one, or you can write E dash. So E dash is equal to V plus IR, and also you can write E dash equal to minus JC if R1, that C is the proportionality constant between your field and your voltage. Now, what we have generally studied in that previous one, that we are habituated to deal with E, that is basically V plus I R plus JXL, correct? So this resultant MMF, we considered it as F R, which was a sum of F naught plus A. Well, now this FR, you can also write that E, although that E is here we should note that this E also is not that way it is exist in reality. Although we talking about it like means casually speaking it as induced EMF, but actually this is also not getting induced across your winding, but we want to incorporate that leakage induced voltage in our account. We say it's an induced EMF. It is not induced. Actually, what physical EMF drop takes place across your circuit, that is V plus IR. So anyway, we are having this. Now what we can have is that the EMF which is responsible for armature leakage reaction, like let me draw it in a virtual manner, that if we have actually this, then actually we could consider this dotted line is showing us the E, and this E is again here I would like to show it by, yeah, here I can show it by a solid line because this is also a means MMF that exists. Basically this is the MMF I should show by dotted line because these actually means do not exist in reality. This FR1, we are just exploiting this hand drawing it, but like in means inside your machine what exists is F0 and A, and any leakage MMF if we consider, that is X. So this is our JIXL, and this side is like our minus AX. So why minus AX? So that we can write similarly that JIXL is equal to minus JC minus X. So basically we can write that if we add these two, then we would get FR, which is holding relation with E. So what we can write is that it's very simple. FR is equal to FR1 minus AX, right? And from these two, if we combine, we get F naught is equal to FR1 minus AX minus A. So this is the whole thing. So once we construct this, then we find out FR1, because somehow we are assuming that this JXL is known to us, and if JXL is known to us, then IJXL drop is also, we are able to figure out IJXL drop, and for that we can we can have an MMF that is minus AX. Then we would, means here basically what physical EMF you are being replacing by virtual MMF, that is FR1. E dash is a physical EMF and it is getting replaced by a virtual MMF FR1. Like FR1, in reality FR1 does not exist. In reality what exists is FR. FR is the total amount of MMF being received by your stator winding. However, it fails to utilize the X amount. Rest it get its FR1. So FR1 is just a like numerical difference. Like in that case, previous case, it was E naught minus E. In case of EMF method, E naught minus E was JIXAS. So that JIXAS is not a physical drop. It is a drop due to armature reaction. So similarly here, but we replaced it by an EMF. Here we replace it by a MMF. So we are getting this. Now how to figure out the regulation, the amount of regulation is that, like if we can make short circuit condition, your like as R is very small, we can say that means one thing you can do is that you can directly deal with E dash, means figure find out E dash, or you can do what, ultimately from this equation you can find out what is your F naught, and obviously you can find out E naught is equal to minus JC F naught. Using this you can figure out the amount of regulation, right? So now let us solve the problem that will make your understanding clearer in this regard. So what does that problem says? MMF method. So This is the phasor diagram. Obviously here it is our E naught. So let us see how this we can use to figure out the regulation. So in MMF method, it is E2 is equal to V plus IR. So if you do it, you will get it is like 3810 plus 218.7 0.8 minus j.6.5. This is R. So E2 or E dash, in our discussion we denoted it E dash. So it will give you 3898 angle minus 1 degree. So basically very small amount. So E dash is equal to that is 6751.5 volt. Now we have to figure out the FR1. What is FR1? This much. So FR1, how to figure out? FR1 we can find out from that curve. Yes. From here we have to figure out for which value of field current is responsible for producing this 6751.5 volt. So where you can get 6751.5 volt? In this book they have taken something like this, say 26 ampere. So actually I can drop all this problem because it won't come. Obviously I cannot give you such graphical things, because in that case everyone will take different values and I have to calculate every time. I'm a lazy person, I will avoid that kind of problem, but this is required because this enhance your understanding, right? So if R1 you will get it is that 26 ampere. As per this book it is 26 ampere. Now what about armature reaction and your leakage reactance? Your armature reaction and leakage reactance to full load circulate the full load current. What is that? Since your when your V is very small, what I am trying to tell you here we will take one approximation. What is that? Since your R is very small and during your short circuit test V is 0, so we can say, or we can neglect IR and consider that total drop is taking place across means what we used to do for your zero power factor. Where is that zero power factor? At least that I have discussed, I clearly remember. Yeah, so yes, that is what I was trying to say. This much, this is responsible for your not only XL plus this is actually that armature reaction and your like leakage reactance. These two, this person is responsible for both of them, right? So if that is the case, we are assuming that this much, this IFSC is approximately equal to A plus AX. So that value is also given. That value was how much? Here in your problem it is given that IFS, yeah, this one is 30 ampere field current. So this is equal to A plus AX. So if this is A plus AX, so your A plus AX is 30 ampere. Now we are all done. Only thing we need to figure out the angle between A and FR1. Same A and FR1, this or minus A and FR1 this much. So how to figure out? This will be same as 90 plus this angle. So this angle we cannot find out directly, rather we know the angle between V and I. This is I, V and I we know. So whatever angle it will have between V and I, will subtract this much angle from that and then add 90 degree. So we will have what? We will have 90. What was the angle between V and E dash? Yeah, minus 1. So 90 minus 1 plus cos inverse 0.8. So this gives us 125.9 degree. So now you can figure out if not, that is if R1 square plus A plus X square minus 2 FR1 A plus AX cos of, say this is alpha, so cos alpha. So if you solve this, you will get F naught is equal to 49.9 ampere. So F naught is equal to 49.9 ampere, almost 50 ampere. So for that 50 ampere current, we need to figure out the value of corresponding E naught. So let us see what E naught we will get here. For 50, this is how much? It is some value. So as per the book, it is 8468. So it is the regulation value is Here we are calculating regulation in terms of line, but there is no harm because line and phase, all of them are just scaled. So whatever regulation you will calculate in terms of line or in terms of phase, you will get the same thing. So here, interestingly, we are getting a very small value of regulation. That is 28.3 degree or 3%. So interestingly, this is what is known as your, that is why it is known as optimistic. Why optimistic? Because you have assumed what is your fallacy here is that, like the previous was pessimistic before because you like when you consider E naught or F naught, at that time you are actually doing what? You are actually doing something that is not possible. Money, if you go in that way, that proportional way, that F naught is actually not possible. E naught is not possible in reality in case of EMF method. You are assuming linear relationship. And here what you are doing actually, you are replacing an EMF by MMF. So what you are actually doing, whatever you are doing just the reverse thing, and that is why if the previous one was pessimistic, now you are going to get an optimistic value. Like whatever regulation takes place in reality, your calculated regulation is smaller than that value. Your actual machine will offer a poor regulation in comparison with the calculated one. How? Let me explain that. Here you are assuming your E naught, you are calculating from F naught, right? So this F naught you have calculated. Now see, while doing so, what you are actually doing, you are taking this one. Where is that graph? Taking help of this graph, but doing so, you are assuming that your whatever transition is here, the drop from F naught to this 26, it is linear. What I am trying to say, you are considering that basically it is all about this slope. So here you are trying to assume that slope is more or less like this. Like in EMF method, you are actually trying to find out slope in this region, and in MMF method you are trying to find slope, means whatever slope you get, it gives you an idea around this region. So you can see that slope of this line, the small the slope of this line, the amount of regulation will be smaller. So it depends which portion of your line you are taking. So in case of EMF method, you are actually doing something that is having very steep slope, right? So that gives you a considerable value of regulation. And in EMF method, on the contrary, you are doing something that is having a small value of slope and giving you a regulation that is actually smaller than what happens, or if you allow the machine to operate under same operating condition, the machine will offer you a regulation that is poorer than what you have calculated using your MMM method. So that is why one is optimistic, another one is pessimistic. So another one we have, okay, now we figure out the power factor, sorry, power angle. The last case, our power angle was some value. Now here we have to figure out the power angle. Well, so let us start with our additivity, means sorry, not additivity, homogeneity. Let us start our discussion on modified MMF method, that is ASA method. So what we have discussed in this problem, that now it is giving us 28.3%, while that one was giving 87.8%. So EMF method 87.8 and MMF method is giving 28.3. None of them are accurate, but that is why another method is proposed, that is ASA method. But what is that ASA method? Let me describe. If we see the phasor diagram once again, what you can figure it out here, the angle that is between these two, like if you see this expression, this minus 1 alpha, if we drop this 1 degree from alpha, then also it will become 124.9 degree. So basically 125 degree and 126 degree, so it won't make much difference, right? So what we can see that, like here, we can see that, yeah. So um, sorry, I have made a mistake here. It is actually and I made a mistake. Just a minute. Let me just check once again. In my copy that, well, so this much, this angle is okay. Now see, this angle is something like 125 degree. So what we can do here is that it was correct. This problem was correct. Alpha is equal to this much. Now, what we can write that, like if we make an approximation that R is small. So if R is small, then what we can do here is that this 1 degree is due to R. So we can drop this 1 degree. And what we can have here is that if R is small, then the angle alpha will become 90 plus theta, right? So basically what we are trying to do is that FR1, what is taken as proportional to your means E dash, now we will take FR1 is means proportional to V. So how we can do that? That is what I am trying to say, is that like here, if we see this figure, So here you can see that this one, it is like, here I have just let me make it just a minute. Where is that paper? Yes. So here what I am trying to say is that yes, that is what I was trying to do, is that a very basic thing, that let us try to understand this one. Actually, what I have drawn here it is like the current I and the field ampere, both of them are drawn in the same scale. This is also our current I is in this direction. Huh? So this is V plus IR. We are getting this one is our E, right? Now what we are doing, this E is equal to what? This E is equal to V plus IR plus JIXL. XL, you can obtain this from your Portier triangle test, right? Then what we are doing, this basically how I have constructed this, like you know V and you know theta. So this OV, when I construct this one, so this line actually I have taken it from a book, because otherwise it will be a bit difficult for me to draw. So first what I did, uh, this is the field ampere, and in that means the horizontal scale is for ampere. Now don't get it confused that field ampere phase. Field ampere is have no phase because it's a DC thing. But if we consider the RMS value, so field ampere and your armature current, both of them can be plotted on a single scale. There is no harm. Now what we are doing here is that we are trying to draw our V. So what about this V? How to obtain this V? See, like here this current is our reference. Now as per our scale, we have drawn this OV, correct? Then as per the procedure and as per magnitude, IR, JIXL, and finally this one OE, correct? Now once we and for that I need Excel, so that is obtained from Portier triangle. Fine. Now this voltage OE, if I just take a means compass and set this much arc and try to draw a arc, then what it will, where it will go? It will go to this point, this arc I am talking about. So this is the point where it intersects OE dash. Now through that E dash I have drawn a line that is parallel to our horizontal axis. This line, right? Now what I am doing, this line is intersecting this OCC at a point. This point is our like this point is B. Then what I am doing, this is my unsaturated region. Basically why the error is either high for both MMF and EMF method, because EMF does calculation based on unsaturated graph and MMF does calculation based on saturated graph. So here we are trying to obtain an average slope. So how we can do so is that, like here this is your like now we are this unsaturated part, it is having a slope, right? So what is that slope? That slope is this is our A and this one is B, right? So what this A and B indicate? Think about it. What does this A and B indicate? This A and B, like, are not they telling us the amount of additional excitation required over our means unsaturated region of means magnetic circuit? If we try to reach that, then this much is required. So this wave dash, this one is like this much we are considering as our MMF method. Sorry, not MMF, that is modified ASA method. Some people say only ASA method, some people say the saturated synchronous reactance method. So there are different nomenclature you will find. Things will become more clearer to you once we solve that same problem using this approach. Just a minute, let me adjust. Now see that we have to figure it out. What is A, what is B, what is OA, this, that, all the things that I have said as of now, how these are relevant to our particular problem. for that I need to go to that image from where it all started. Yes, this one. So here, no, not this one. I think I have made a mistake with that image. Yes, yes, this one. Yeah. So what we can see from here is that uh, this is our, let me try to first remove all the unnecessary things that we are having here. Yeah, basically this much we need to just figure out that this is our A and B. This is A, this is B. So we have to figure out the amount of regulation. Now go back to our original page where we need to do it. So what is your V is equal to? We know it is line to line voltage 6600 volt. Once again, just let us see it. When we will get that much voltage, 660 volt, perhaps we will get it for some value that is 21 ampere, right? So one thing we can do is that let us just hijack this one to our that page, otherwise it will create problem. Yes, that's better. So now it is clear that 6600 you will get in this value 6600 somewhere here. As per this present calculation, they have taken this much is, this is our FR1 is equal to 21 ampere. What is our FR1? Basically FR1 is something that is responsible for E dash, but as I have mentioned that we will neglect this IR and we will consider that E dash is approximately equal to V. So FR1 becomes proportional to V. Therefore we got this value. How it comes. Well, so FR1, we already know the value of A plus AX, that is 30 ampere. So angle between these two guys, that is just 1 degree greater than the previous one. So what you will get here is that that your, let me draw a simplified picture that you will get it clearly. In terms of phasor diagram, we can draw, say this is our FR1, this is our minus A plus AX, this angle is that what we found in MMF method, that is 126.9 degree. This angle is right, and this much is responsible for your voltage generation. So if this point is O, so let this be F naught. Now this F naught, we can write, what we can write is that like this F naught square is equal to your basically we will have here. So if you do this simplification, you will get F naught is equal to, it is coming around 45.8 ampere. This one is 21, these two together is 30. So if you put the value, you will get 45.8 ampere. Now this voltage means we have to figure out the voltage induced in the air gap. The voltage induced in the air gap will be how much? That is your Just a minute. So now air gap induced voltage, let me write it, otherwise you will miss. Air gap induced voltage in terms of circuit, you can consider it is like so what it says, how much it will be air gap induced voltage, it is 3810, that is V, plus your 218.7 I, then the power factor, then your R 0.5 plus JXL 3.4. So together this gives us how much? Together this gives us 4344. So the magnitude of this much is 4376. Now for 4376, what we need is that we have to figure out the line voltage. That will be 4376 into root 3. So total it will become 7580 volt. Now we have to figure out the corresponding current for 7580 volt. So the corresponding current for which we can expect 7580 volt, 7580 means somewhere here. So 7 So this 7580 we will get it for how much? It is like here means this is our B and this much is our A. So we have to measure this one, right? So this one, how much this one will be? This one will be something that is from the diagram we have to measure. You have to take a scale to draw perpendicular from A and B. As per the book, this much is 10.8. Okay, so once you get this 10.8, then what is required is that this means what was your previous value of your current OF or F naught? F naught was 45.8. Now as per MMF method, sorry, as per ASA method, we need to change it like F4 F4 plus this F dash. So that will be 45.8 plus 10, that is around 56 ampere. Now for this 56 ampere, what would be the induced voltage? Here you will get the voltage, induced voltage. This is something, as per the book, it is 8660 from OCC card. What is your voltage in load condition? So this gives us, right? Therefore, it is clear that we are having this much percentage of regulation. So now if you compare all this percentage of regulation, you will see that for EMF method it was 87.8, very high. Here it is 28.3, very small. Now here this one is 31.2%, like slightly higher than the MMF method and slightly lower than the EM, means considerably lower than the EMF method. So this one is quite close to your actual values. Anyway, now we have to figure out the power angle. So power angle, finding power angle for EMF method is very easy. That is the only benefit of EMF method. Its power angle is very easy. Like you can get it readily here. That is 26.94. So now for MMF method, how to figure out the power angle, because we have not yet calculated E naught in terms of magnitude. Everything was calculated in terms of this. But what we can, what is our power angle? The definition of power angle remains same. The angle between V and delta, E naught and V. But as this diagram has drawn in proportional scale, what we can say that this triangle, like if you form a triangle here, with side E naught, E dash and the line joining the tip of E naught, E dash with this one FR1, F naught and this dashed line, then what you will get actually, you will get something that is these two triangle, their angles are identical, like they are similar triangle. So whatever angle you are having here, the same angle you are getting here. Therefore this one, like the angle between E naught and E dash is equal to angle between FR1 and F naught. Now you have already know these three sides of this triangle is known to you. So from that you can calculate what are the three sides. FR1 26, this one is 30. So now you can figure out the, let us do it here only, otherwise people will get confused. uh, so we are looking for delta. So this side is 30, this is 21. So how much this side will be? We can figure out. It will coming something around this side, and also this, like this side is how much it is. We have already figured it out. Probably it was 49.9, right? So if it is 49.9, then we can figure out this angle between these two, that is 21 and 49.9. So this will be, if you apply trigonometry, you will get it is 29.1. Now this much 29.1 is here between E naught and E dash, but V is 1 degree closer to your E naught than that of E dash. Therefore angle between V and E naught is 29.1 minus 1 is equal to 28 degree. That is delta in your MMF method. So another thing what we are getting here, that is also interesting to note, that your power angle is increased using this MMF method. Why so? What is the physical interpretation of power angle, that we will discuss. But obviously, as the name power angle or torque angle, it implies that it is directly proportional to some power. So if it is proportional to some power, then means it clearly indicates that MMF method gives an idea that your machine is delivering more power, right? Or means is MMF method is trying to portray an image that your machine is delivering more power. Okay, now what about that ASA method? The power factor angle, power angle. The power angle in case of ASA method will be between this 30 and this side is 45.8 and this side is 21. So obviously we can expect that this angle will what will happen, that see these 30 and 21 remain same, but if you reduce one side of a triangle, then angle opposite to that side will automatically getting reduced. So instead of 40, what it was some 49, if you make it 45.8, it is getting reduced by 1 degree. So what changes you can see here, you will be able to see Here this one is increased by some portion, that is some 31.6 degree. So this one is becoming and that is your power angle, right? So as per this ASA method, your power angle is 31.6 degree. So now we have to figure out the short circuit ratio. What about the short circuit ratio from the card we need to figure out? So rated voltage at which current it can produce the rated voltage during open circuit condition. It is somewhat your 25 volt. Your rated open circuit voltage is 660. So at 25 volt you can expect 25 field ampere you can expect rated voltage. So this is 25 ampere and the SCR will be how much? 25 by 30, that is your 0.866, right? So SCR is 0.866. Okay, so this is our SCR. Now, as I have discussed, another things that you should not forget, that is somewhere in the past I have discussed that what is your ZS? ZS is, as it is very small, your R. So what we can consider that from that result you will get in EMF method the value of ZS was something like 18.9 ohm. Now what about Z base? Z base is equal to your 3810 by 218.7, that is base voltage by base current. So that will give us something 17.42. So what is our ZS per unit? That is our, this is not in calculation but I am doing it for your means concept clearance, means clarify your concept. We will get it like 1.085 approximately. Now the question is, that is a bigger question. So if we do SCR from here, what we will get, SCR is equal to 1 upon is 1.085. So what we will get? So this SCR is higher than the calculated one. So which one is true, or both of them are true, or there is some logical means I have means made intentional mistake, or means both are true. So think about it, and please update me about your decision. We can have a good discussion on this, that SCR calculated from ZS per unit and SCR calculated from graph is too different, but we have already proved that they are like so what is the case? Anyway, now coming to the last part of the problem, that for power factor 0.5 lagging and 0.5 leading, these are the two extreme cases. Like determine the range of field current by ASA method for rated terminal voltage at full load with power factor varying from 0.5 lag to 0.5 lead. So actually these problems are very boring, but we have to do it anyway. For power factor 0.5 lagging, and what is your cos theta? That is theta pf is equal to 60 degree, right? So that angle will be so your f naught will be this is for lagging. Now for leading, what you will have? You will have your E is equal to sorry. we have to figure out E. So what is the value of E we will get? E will be 4517 volt. So if it is 4517 volt, then that will be how much? Root 3 into 4517, that is 7824 volt. Let us go to that card now. How much is responsible for your 7824 volt? Uh, 7824. Then we have to measure this gap. Previously for 7580 it was 10.8. I think well, as per the book it is 7 ampere. You can check whether it is 7 ampere or not. As per the book, for 7824 volt, the gap between A and B is 7 ampere. Right. So let us consider that 7 ampere, then what you will get is like now. If that is the case, then again what we need to do is to figure out that Okay, so here our question is that we have to need to figure out the field excitation. So this is extreme field excitation for 0.5 lagging. Then we have to figure out for 0.5 leading. So for 0.5 leading, similarly, so what it will result? It will result something E is equal to magnitude wise 3255. Previously it was 4517 352255. So this is for 0.5 leading. So 3255 into root 3 will becoming how much? 5638 volt. Now for 5638 we have to check where do you get 5638. So this will be our A, this will be our B. So as per the book, this gap is 0.7 ampere. So the net excitation required will be okay. Another thing we need to figure out is that if not for 0.5 leading will become 21 square plus 30 square minus, this is a change, here it was plus, now it is become minus. So you will get what? You will get this is equal to 15.8 ampere. So net will be how much? If not plus 0.7, that is your 16.5 ampere. This is for 0.5 leading. So this is the completion of this marathon problem. Okay. Okay, now let us go to our next problem. That is, let me share another image. Like in this chapter, reading data from image is extremely important. So obviously during examination I may not give you this kind of problem because of there are certain space constraint, and obviously this will consume a huge amount of page also. Shape paper, shape trees, we should consider that also. So, but why I am means trying to share the solution with you is that So you can understand at least how to solve such problem. So 1.5 MVA, 11 kV, 3 phase, star connected, effective resistance R is equal to open circuit and core loss are here. So we have to figure out the for 180 this voltage is 11800, right? And for that the corresponding terminal voltage is here, like if we extend it, it is 14250. Then for 160, sorry, 140, it is 13200, or 140 it is for 110, this point is 11870. Then for 50 it is 6650. For 40 this much is 0. So 2 point on our 0 power factor is mentioned. Now let us try to solve this problem. So first, how should we proceed? What we can do is that we can consider the short circuit characteristics and complete the 0 power factor characteristics. Here it is already there. I will show you how to construct. Now we have to find out the means that regulation, power angle or torque angle delta, and efficiency on full load at a power factor 0.8. Means what we need to do here, okay, let me write, otherwise field circuit resistance machine mechanical and tray load loss is equal to 15 kilowatt. So let us start with the solution. So solution, I will draw a truth picture and then we'll go to the final one. Like rated terminal voltage will be how much? So they have already drawn the curve, but I would not like to show you the curve. Rather, I would like to explain that if that curve is not present, how to construct it. Because what is actually asked in this question, however, there is only one picture is given, so it is difficult to means it was difficult for us to get those data without that curve. So now from the data of ZPF, what we can see that IF is equal to 40 ampere. We can even write the data what is there. We have got like this is IFL, this is OCC, this is core loss. For the time being, let us keep core loss aside, and ZPF VT means terminal voltage. So for 40 it is some value 0, for 50 it is 6650. The value is not specified because only two values are there. So two value for two ZPF is given. So how we can construct it? This is my IFL. Now for different value we need to plot. So say 51 value is given, that is 6650. Then for 110, here 110 another value is given, that is 11870. Then another value is given for 140, that is 13200, and finally at 180 it is something 14250. So once you get this, you should join a curve like this using freehand diagram. Okay, now you know two extreme cases, like here at 40 you know and for 180 you also know that is given, that is 11.8. Just a minute. 11.800. So these two extreme points are given. Now we need to construct the ZPF. So how we can construct that? So IF is equal to 40 ampere is required to, means after that means a 40 ampere produces full load current on your short circuit, right? So this much is producing full load current, because one thing in our ZPF is that we always keep our current is equal to the full load value of the current. So that means 40 ampere is the minimum value of current from which our ZPF can start. Now in that short circuit characteristics, what we know, that generally armature resistance is so small, our armature means leakage and this armature reactance, they are producing almost means complete demagnetizing action. So we can say that during that the power factor of the armature current is 0. So short circuit current, how much will be there? Short circuit current will be 78.7. And also that is the IFL. This one, right? Now what we know, that this short circuit current, let us means what we do in the first lecture number 2, we can draw the here this side. If we use this side for our voltage scale, this side we can use for our current scale. Now at 40 the value of current is 7 what is 78.7. so say this is our that your 80, this is current scale, 40, 120, 160, like that. So at 40 ampere field it is 78.7. And what we know, that short circuit characteristics is a straight line. Once you get one point, it is sufficient for you to draw a straight line through origin, because short circuit characteristics is always a straight line passing through origin. So this is your SCC, this red one is your OCC, we need to construct your ZPF, right? Now we need to draw that one line, that is our, let us consider this, oh, sorry, this gentleman, this was on ZPF extreme. This point is how much? 11800. So this gentleman is our point B. So this is point B. Now we need to draw the line from B, that is of having length is equal to BC. So what about the length of this BC? This is also 40, right? Now, well, this is BC. Now from this point C, let us draw a line that is parallel to our air gap slope line. So if this is our air gap line, so this one. Now, if this is the case, then this point is D. Now, let us join this D with B and draw a perpendicular on BC from this D, right? Now this DE you need to measure. What is this? This one is JIXL as per our, or means J, sorry, not J, it is IXL. So if this is IXL, then you can find out that. Now one thing you must keep it in your mind, that whatever data we are giving you here, this side is your line voltage side, right? So whatever reading you will get, this height of this triangle or the height of this DE, that should be root 3 IXL. So that is, as per calculation, it's 900. So XL will be 13.9 ohm. And the armature reaction at full load will be how much? This much. That is BE. So this BE, if you measure, it is 24.5 ampere. Now And how you can like do this means complete this zero power factor characteristics. If this is your dB, you can take any point on this OCC and draw lines parallel to this dB, right? Take arbitrary point on your OCC and draw parallel lines of length dB and then join all of them to find your zero power factor characteristics. The diagram that is drawn in scale is this one. So all these are parallel to your dB, right? So we are doing it. Another way you can do, that is also possible. Once you construct this triangle, you can slide this triangle keeping D on this OCC, the same thing I am telling you, and ensuring this BC remains parallel to the horizontal axis. So it will be like somewhere then you further you are keeping D on this, or you can in this way you can construct this ZPF. Fine. Now we have to find out the other details. I think you should be able to do the calculation by yourself. Still, let me do it. The voltage, induced voltage will be just a minute. So this one is how much? This one is 0.8 minus j 0.6. This one is 0.7 plus j 13.9. After doing this sort of mambo jumbo, what you will receive? You will receive fruit of all this calculation will give you your power angle. No, sorry, not power angle. This will give you the E line will be how much? Now here we need to calculate the E naught. So for that we need F. So how we can find out F? F is like angle between E and V. So here your FR, for this much voltage you need to find out corresponding FR. For that we go to refer this scale diagram. So for this 12300 volt, 12300 volt, uh, 12300 volt, you will get 12300, so somewhere here. As per this book it is 118, but we can take some other value. In my opinion we should take 105. So anyway, you can take any value you want. So as the calculation is given, if you follow my reading, then it should be 105. So anyway, reading doesn't make much means change in our insight. And this much will be 0.69. So this will result you whole 136.1 ampere. So this is F naught, or F means the original open circuit F. So for this you need to figure out what is the, for 136 it will be here. So around 13,000. So in this, as per their calculation, this voltage is corresponding voltage. So this should be, the regulation value is 13100 minus that is 19.1%. Okay. Now the power angle will be how much? Power angle will be this one is 90 plus cos inverse 0.8 plus, what was that angle, 6.8. This side was 24.5. This side is 118. This side is 136.1. So you need to find out this side. Well, so it should be something, if you calculate, it will be 14.3 degree. And figure it out. oh sorry, this will be as per their calculation. This one is 7.5. Now this fr is let me show you what I'm trying to tell. That what is that MMF method diagram? Yes, here you can see that this one was angle between FR1. Now in zero power factor method we can find out angle between this. This is coming 7.5. Now obviously in our case, so obviously this 7.5 for corresponding value of E naught it is 90 degree, right? And E is 90 degree with this one. So these two we can say from this that angle between E naught and E is 7.5 degree, right? So therefore well, let me draw the picture, otherwise, perhaps you are not getting my point, what I'm trying to say. V, I. This is theta, this is IR, GIXL. This is E, this is FR, 90 degree. This is your minus A, and this is your F naught or F, which is responsible for production of, let me use different color. We need to measure this angle. What is this much? This much is 6.8. We are getting this much is 7.5 degree. So therefore, if we compare this two, then this is our E, this is V. So this much is how much? This much is 7.5. So total angle will be how much? That is the delta will be okay. Now we have to figure out the efficiency. So for efficiency, first we need to figure out the loss. So armature copper loss would be how much? 3I square R. The armature copper loss. So this will be 3 into 78.7 square into 0.5, sorry 0.7. So it will be somewhat 13 kilowatt. I'm just copying the data from the book. Core loss for induced EMF. Now here there is a big not big, rather a subtle understanding we must consider here, that for finding out core loss, which value should we consider? Which will be responsible for our core loss? See, core loss is caused due to your air gap flux, and air gap flux is proportional to not your open circuit voltage, rather your induced voltage E. So you have to consider the value of E. Say here, what is the value of E? E is this much. For this we have to figure out the core loss from this diagram. So 1230 somewhere here, so core loss will be some 17.4 kilowatt as per their means diagram. Like how you should figure it out? Still I am getting a higher value. Probably they are having some, like they have not taken the data correctly. Have we taken the data correctly, we could get some other value. So it is like that only. Like straight you have to figure out. Only thing you need to consider that you are measuring E. When corresponding to E, you should figure out the core loss, not for E naught. So your hysteresis loss, sorry, not hysteresis, both core loss other losses, field loss, is your so it is 136.1, because this much current must flow through the field ampere, so into 0.5 that was given, so it is coming 9.3. So total losses output is equal to so efficiency okay. Now let us consider the last problem, that is some data is given for a three-phase cylindrical rotor synchronous generator that is having an armature resistance R is equal to 0.02 per unit. This is very important, per unit. Leakage reactance XL is equal to 0.10, again in per unit, and unsaturated synchronous reactance. Eight per unit. So the generator means load, supplying a load PA at uh, the generator is supplying full load with power factor is equal to 0.8 per unit. Sorry, power factor is what is my bad. So full load power factor point with power factor 0.8. This is our load specification. Well, then we have to determine the excitation voltage and load angle. Also known as open circuit induced voltage, or denoted by quite often E naught. And the saturation factor K. So K can be read from this table. Two point four. So this is saturation factor K. How to use this K and why should we consider this problem, that I will discuss. But let me take this to our next page. So what is saturated and unsaturated synchronous reactance, that we need to know, right? So here one thing you must understand, that what is saturated and unsaturated synchronous reactance. For that I would like to share a card with you. I am not sure whether I have taken a snap. Just a minute. So this was the curve I was talking about. You can see here, and it's quite clear that if you consider the value of synchronous impedance, first at the linear region, it remains almost constant as long as your voltage and means open circuit voltage and means current, it's like they are proportional to each other, means oh sorry, not proportional, rather they are like following almost linear characteristics. But once that is there, then what would happen, it would follow a kind of hyperbolic relation with increasing current, because increasing current won't cause much change in your induced voltage but would change the short circuit current, right? So that is how your synchronous impedance will vary. So this is in this region, this one is your unsaturated synchronous reactance, and this side is your saturated synchronous reactance. If you can recall that there was in last problem, there was some difference between the synchronous reactance calculated from SCR and the synchronous reactance per unit value and synchronous reactance per unit value calculated from SCR. So now you have to think about that and you have to give me the answer. Well, you cannot, you are free not to give me the answer, but means that is not a way how things should work. So basically what I am trying to say, that as you are, the whole concept of synchronous impedance is to replace your replace your MMF by a virtual reactance, but this one is, as I have already mentioned, that EMF method generally acts on based on the linear region, or means where the OCC curve is very steep. In that region, based on that region, it gives regulation value, and that is why we are getting such a high value of regulation. And on the contrary, if you consider your MMF method, it consider saturation region of OCC, and that is why it gives a very small value of your regulation. So this is same is true for synchronous impedance, that we can see here. We can have two different value of synchronous impedance, namely one is in this region, that is saturated, and here in this region, that is, sorry, this one is saturated and this one is unsaturated. Now to figure out means acceptable relation between saturated and unsaturated, what we do, we write that at any point x is right. So first you need to figure out the value of E from this. So E you can calculate from the given data. So these are the data for your E, and interestingly, for calculation of E, you don't need your this gentleman, you do not need, only XL is sufficient. So E will be how much? V plus I cos theta plus J sin theta so that would be something like 1 plus 0.8 minus j 0.6, here it is 0.02 plus j 0.1, so eventually it will result you 1.078 3.62 degree. So this 1.078 is very important for us. From this we have to figure out the value of K. So it is 1.56 and 1.1. Now for 1.08, what we can take? We can take an intermediate value, that is, or means you can just do linear interpolation kind of things like so. If you do this kind of calculation, it will give you the result and you will get something that is approximately equal to 1.77. So then the remaining things is very simple. You just need to put the formula, and X is saturated will be 0.8 minus 0.1 by 1.77 plus 0.1, that is 0.55. Then you can calculate E naught. How E naught can be calculated? E naught is equal to, here you put this value. So instead of 0.1, now you put 0.55 here. So doing that, you will get 1.412. This will be 17.64 degree. So that's it. That is all for this lecture. Next video we will solve all the